Hello, everyone. So last time we looked at the concept of limits. The limit of a function. So we defined the right limit and left limit. And left limit. So right limit means as x or the input x gets closer and closer to a from right, meaning that if x is bigger than a and gets closer and closer to a, what happens to the outputs? If they get closer and closer to some fixed number L, then we say limit f of x as x approaches to a from right is L, or we just say right limit is L at a. And similarly, left limit means x is smaller than a and gets closer and closer to a. And we saw that a limit f of x as x approaches to a exists if and only if exists and is L, let's say. If and only if right limit and left limit both exist and equal to L. If both right and left limit exist and are equal to the same number, then the whole limit exists and is equal to the same number L. But if right limit or left limit do not exist, one of them does not exist, or if they both exist but they are equal to the different numbers, they are not equal to the same number, then the whole limit will not exist in this type of situations. All right, so now today we want to look at computing to 1.4, computing limits. So far, we said to compute the limit, let's say limit f of x as x approaches to a. So you have to imagine values of x get closer and closer to a, look at the outputs and see whether you can find any pattern. Are the outputs getting closer to and closer to any fixed number or no? So that's one approach, but it's time consuming because you have to find, for example, let's say you want to find limit f of x as x approaches to 2. You have to find f of 2.1, then 2.01, 2.001, and so on. At the same time, you have to look at f of, for example, 1.9, 1.99, 1.999, and so on. So it's time consuming. But we have some laws or rules or theorems that can help us to calculate the limits much faster. So the goal is to compute limits using limit laws. So the first theorem I want to say, and let's say part 1, if p of x is a polynomial, then limit p of x as x approaches to a is equal to p of a for any real number a. Seems that the screen is freezed. Okay, now it's good. So if P of X is a polynomial, then limit P of X as X approaches to A is equal to P of A. So this is what I also used last time, and I promised you that we are going to state this formally as a theorem. So if you want to calculate limit of a polynomial, it's extremely easy. You just need to simplify P of A or replace X with A. So you're probably wondering that are we always allowed to do that? Well, we saw previously that no, we are not always allowed to do that for an arbitrary type of function. So for many types of functions, to calculate the limit, we are not allowed to replace X with A. But if the function is a polynomial, which is a simple and important type of function, then yes, for finding the limit, we can just simply replace X with A. So for example, let's say if you want to find the limit, let's say 5 as X approaches to 2. This is equal to 5, right? Since P of X equals 5 is a constant function, right? Is a constant function, i.e. a polynomial of degree 0. So constant functions means functions that, the output is always the same number regardless of the input. Now, P of X equals 5 is a constant function, and any constant function is a polynomial of degree 0. You know that each polynomial has a degree. Degree means highest power of X. So if it's a constant function, highest power of X is 0, and so therefore degree of a polynomial, degree of a constant function as a polynomial is 0. So since this is a constant function, i.e. polynomial degree 0, and so by theorem above, we can say that limit P of X as X approaches to 2 is equal to P of 2. And P of 2 is also 5. Again, remember, when we have a constant function, the output does not depend on the input. So no matter what input you use, the output is always the same. So here the output is always 5, no matter what input I use. So P of 2 is also 5. Or another example, let's say limit X squared plus 3X, X approaches to 4. So here P of X is X squared plus 3X. So P of 4 will be 16 plus 3 times 4. And this is 28. So P of 4 here is 28. So you can also, so this is because the theorem allows us to replace X with A to calculate limit P of X, right? So by this theorem, we calculate the limit and it turns out to be 28. But if you want to calculate the limit without using this theorem, you can also, replace X with, for example, 4.1, look at the output, then 4.01, 4.001, and so on, look at the outputs. And on the other side, you can look at 3.9, 3.99, and so on, look at the outputs, and you will see that the outputs get closer and closer to 28. Okay, so this is one important type of, one important theory and one important property. Now look at another property. If, let's say, f of X equals P of X over Q of X is a rational function. Rational function, I think if you remember from pre-calculus, means a polynomial a polynomial divided by another polynomial, and then we can say that limit f of x, which means limit p of x over q of x as x approaches to a, is equal to p of a over q of a if q of a is not equal to 0. Okay, so if q of a is not 0, in this case also, so we saw that in the first property, we saw that if you have a polynomial to calculate the limit, we can replace x with a. Now, if you have a polynomial divided by another polynomial, and we want to calculate the limit, still we can replace x with a as long as q of a is not 0. So if q of a is not 0, then we can still just simply replace with x with a. So for example, let's say limit 2x squared plus x minus 1 divided by, let's say, x squared plus 3, for example, x squared plus 3 as x approaches to 2. So here this is 2 times 2 times 2 squared plus 2 minus 1 divided by 2 squared plus 3. Because, you know, here again, here p of x is 2x squared plus x minus 1, and q of x is x squared plus 3. And then this is 4 times 2, 8 for 10, 9 over 7. And note that q of 2 is 7, which is not equal to 0. Okay, so we have a polynomial divided by another polynomial, and to calculate the limit, we can just replace x with a. Now, the important question here is, what if q of a is 0? Okay, what should we do if q of a is 0? If q of a is not 0, it's very straightforward. We know how to calculate the limit. What about if q of a is 0? What should we do? So I want to recall one fact from pre-calculus, that if q of a is 0, if q of x is a polynomial and q of a is 0, meaning that if a is a root for q of x, then x minus a is a factor for q of x. So if x minus a is a factor, that means, you know, you can factorize q of x as x minus a times another factor, and then try to calculate the limit. So so in this case, first factorize q of x in the form x minus a times another polynomial then so we can have different possibilities. Then consider the following cases. So case 1, if p of a is also 0, then factorize P of X in the form X minus A, again, times another polynomial, and simplify, and then compute the limit. Case 2, if P of A is not equal to 0, then limit P of X over Q of X as X approaches to A is equal to infinity or minus infinity. Find out about the sign by analyzing each factor in numerator and denominator. Okay. So let me give you some examples. Let's start the very simple one. Find limit, let's say x squared minus 4 over x minus 2 as x approaches to 2. So what are the polynomials here? So here, P of X is x squared minus 4, and Q of X is x minus 2, and Q of 2 is 0. So see, the theorem told us that when we looked at the theorem, told us if Q of A, if denominator at A is not 0, just simply replace X with A, very straightforward. But if Q of A is 0, then we have to look at P of A. Is that also 0? Or that is non-zero? If P of A is non-zero, Q of A is 0, the answer is infinity or minus infinity. We have to find out about the sign. But if P of A is also 0, then we have to factorize top and bottom, each one in the form x minus A times another factor. Because remember, from pre-calculus, we know that if you have a polynomial and if x equals A is a root for that polynomial, then x minus A is a factor for that polynomial. Okay, so Q of 2 is 0. Also, P of 2 is 0. So we are in case 1 above. So factorize top and bottom and simplify. So limit x squared minus 4 over x minus 2, x approaches to 2. So I have to factorize each one, top and bottom, as x minus 2 times another factor. So obviously top is x minus 2 times x plus 2. And bottom is just x minus 2. I don't need to do anything. It's already x minus 2 is already there. So this will be an x approaches to 2. Now I want to cancel this factor with this factor. Why are we allowed to cancel x minus 2 factor from top and bottom? We can cancel x minus 2 since x approaches to 2. So x not equal to 2. So x minus 2 not equal to 0. Because if you want to cancel a factor from top and bottom in mathematics, when we have a fraction and you want to cancel a factor from top and bottom, you have to make sure that that factor is non-zero. If it's 0, then you are not allowed to cancel it. But can I say that x minus 2 is non-zero? Yes, I can say x minus 2 is non-zero. Why? Because x approaches to 2, right? X approaches to means x is getting will get very close to 2, but not equal to 2. So if x is not equal to 2, x minus 2 will be not equal to 0, and therefore we can cancel. And then we are going to be left with x plus 2 as x approaches to 2. Now this is a polynomial. And for polynomial, we already know how to calculate the limit. So this is 2 plus 2, which is 4. Because x plus 2 is a polynomial. Again, remember the very first rule that we mentioned was that if we have a polynomial, to calculate the limit, simply replace x with a. So x plus 2 is a polynomial, and to calculate the limit, we should simply replace x with 2. We got 4. Okay, so well, that's it. So now let's look at another example. Find limit x squared minus 3x plus 2 divided by x squared minus 7x plus 6. X approaches to 1. So here p of x is equal to x squared minus 3x plus 2. Q of x is equal to x squared minus 7x plus 6. Right? And Q of 1 is 0. So we said if Q of 1 is 0, then we have to look at P of 1. Is that also 0 or no? So P of 1, so also P of 1 is also 0. So we have to factorize. So again, we are in case 2. So case 1, factorize top and bottom, and simplify. So we get limit x squared minus 3x plus 2 divided by x squared minus 7x plus 6. And then this is limit x approaches to 1, x minus 2 times x minus 1 divided by x minus 6 times x minus 1. And then cancel this with this. So then we are going to get 1 minus 2 divided by 1 minus 6. So that's 1 over 5. Okay, because when we cancel x minus 1, again, this is not 0 because x is not equal to 1. Then we are left with x minus 2 over x minus 6. Maybe I can also include that step, that middle step here, just to be more clear. So see, after you cancel x minus 1, you're left with x minus 2 over x minus 6. X approaches to 1. Now, this is a rational function where top and bottom, each one at, well, especially it's important the bottom. The bottom has to be non-zero at the point so that we can use this rule. Look at here again. we saw that for rational functions, we are again also allowed to simply replace x with a as long as denominator, the bottom function, is not 0 at a. Well, here, the bottom function is x minus 6 at 1 is not 0. So let me say by theorem 2 above, we can write this one as 1 minus 2 over 1 minus 6, because, 1 minus 6 is not 0. So we can say this is minus 1 over minus 5. And then this is same as 1 over 5. Okay, another example. What about, let's say, if you want to calculate x squared minus 3x plus 2, again, divided by x squared minus 7x plus 6, as x approaches to 2. So at 2, what happens? So the top would be 2 squared minus 3 times 2 plus 2 divided by 2 squared minus 7 times 2 plus 6. So this is 6 minus 6 is 0 over 10 minus 14 is minus 4. So can we write this as 0 over minus 4, which is 0? So do you think this is okay, or do we need to factorize something maybe? So the previous example, we had the same function, but x was approaching to 1. So see, please remember, when you calculate the limit, of course, the function is important, but the value of a is, of course, important. X approaches to which number? So previous example, we had the same function with x approaching to 1. And because when x approaches to 1, denominator at 1 was 0, then we had to use the recipe that we mentioned in case 1, where if denominator and numerator both are 0 at some point, we have to factorize. Now here, however, same function, but x approaches to 2. At 2, well, as you can see, denominator is non-zero. Numerator is 0 this time, but denominator is non-zero. So that means we don't have to factorize or anything, because in the very first rule that we said, actually second rule, we mentioned about rational functions. We said that as long as denominator is non-zero, just simply feel free to replace x with a. See, this rule does not, the only requirement in this rule is that the denominator at a must be non-zero. If numerator is 0, that's okay. So according to this rule, we can just simply replace x with a. So maybe I can say, mention here that by theorem 2 above, since 2 squared minus 7 times 2 plus 6 is not 0. Or another example, let's say, what about again the same function? This time x approaches to 4. So this is 4 squared minus 3 times 4 plus 2 divided by 4 squared minus 7 times 4 plus 6. How much is this? 16 plus 2, 18 minus 12 is 6 divided by 22 minus 28 is minus 6, which is minus 1. So again, that's okay. Again, we are allowed to replace x with a. Again, because denominator is not 0 at the point. So as long as denominator is not 0 at the point, just feel free to replace x with a. So again, I can say by theorem to above, since 4 squared minus 7 times 4 plus 6 is not 0. So as long as denominator is not 0, everything very straightforward. If denominator becomes 0, then you have to look. If denominator is 0, is numerator is also 0? In that case, simplify both, factorize both, top and bottom, x minus 8 times another factor, and simplify. If denominator is 0, but numerator is not 0, then this is what we called it as case 2. We said that the answer will be infinity or minus infinity. And we can figure out about the signs by analyzing each factor. We haven't given an example of that case number 2 yet. Now I'm going to give you an example of that case. Let's say again the same function, x squared minus 3x plus 2 divided by x squared minus 7x plus 6. This time x approaches to, let's say, 6 from right. X approaches to 6 from right. What are we gonna get? So this one, so first let's replace x with 6. So 6 squared minus 3 times 6 plus 2 divided by 6 squared minus 7 times 6 plus 6. So this is 42 minus 42, denominator is 0. Numerator is 38 minus 18. 38 minus 18, so that's 20. Numerator is 0, numerator is non-zero, denominator is 0. So that means we are in so this one is 0. This one is not 0. So we are in case 2, what we call it as case 2. So maybe let me mention it this way, that so here p of x is x squared minus 3x plus 2. P of 6 is 20, which is not 0. Q of x equals x squared minus 7x plus 6. Q of 6 is 0. So we are in case 2 above. So in case 2, we said you have to find out about the sign, whether positive or negative. So because the answer will be either infinity or minus infinity. So let's see, limit x squared minus 3x plus 2 divided by x squared minus 7x plus 6. X approaches to 6 from right. So this is limit x squared minus 3x plus 2 divided by x minus 1 times x minus 6. X approaches to 6 from right. So now this is, the top is 20. Bottom is 5. 6 minus 1 is 5. And then 6 plus minus 6. 6 plus minus 6. 6 plus means a number a little bit bigger than 6, like 6.1, 6.01. Minus 6, the answer will be 0.1, 0.01. So the answer will be a little bit more than 0. So 0 plus. So this means a number a little more than 0. So then the answer with 20, so everything is positive, right? So 20 over 0 plus 5 times 0 plus means 0 plus, because 5 times a very small number and a small positive number is still small and positive. 20 over 0 plus, the answer is infinity. Why 20 over 0 plus is infinity? 20 over 0 plus means a very small number but positive. For example, 0.1. So for example, 20 over 0.1, that's 200. Or 20 over 0.01, this is 2000. 20 over 0.001, this is 20,000, and so on. So see, as the number denominator gets closer and closer to 0, the output becomes larger and larger. So that's why 20 over 0 plus will be infinity. Maybe I can mention here that note a positive, a fixed positive number over 0 plus is plus infinity. Similarly, a fixed negative number over 0 plus is minus infinity. For example, minus 6 over 0 plus, this is minus infinity. Because like minus 6 over 0 plus means like minus 6 over 0.1 or minus 6 over 0.01. So the answer will be like minus 60 or minus 600, minus 6,000. So which will be minus infinity. And similarly, a fixed positive number divided by 0 minus, this is minus infinity. And finally, a fixed, so for example, let's say for example, 8 over 0 minus, this is minus infinity. And finally, a fixed negative number divided by 0 minus, this is positive infinity. So for example, let's say a minus 3 over 0 minus, this is positive infinity. Okay. So as an exercise, for example, the example above, find limit x squared. So let's say same function, x squared minus 3x plus 2. Over x squared minus 7x plus 6. Now, if this time if you calculate the left limit at 6, so the answer, you will see that it will be minus infinity. Right limit, we saw that it was infinity. Left limit, we will see it's minus infinity. So note examples above show that x equals 6 is a vertical asymptote or VA for this function x squared minus 3x plus 2 divided by x squared minus 7x plus 6. Vertical asymptote, we said last time, means a number a such that limit of the function at a, either the left limit is infinity or the left limit is minus infinity or the right limit infinity or the right limit minus infinity. So if at least one of these 4 conditions holds, then we call x equals a as a vertical asymptote. So here, the left limit at 6 is minus infinity, the right limit at 6 is infinity. So two of those four conditions hold, and therefore x equals 6 is a vertical asymptote. Now another example, find limit x squared plus 7 divided by 4 minus x squared, x approaches to 2 from right. So if I replace x with 2, what do I get? I'll get 4 plus 7 divided by 4 minus 4. So the answer will be, so 4 minus 4 plus, basically, right? Because x is approaching to 2 from right. So 4 minus x squared, if x approaches to 2 from right, x squared will approach to 4 from right. So 4 plus 7 over 4 minus 4 plus. So can I say this is 11 over 0 plus? And the answer is infinity. Do you think this is correct? Four minus 4 plus. And the numerator is 11, so the denominator is 0 plus, and 11 over 0 plus is infinity. This answer is not correct. See, many people, many students think that it's a very common mistake here and common misunderstanding. They think because this is 2 plus, then this one should be also 0 plus. We don't have such rule. You have to think about the concept. What is the meaning of 2 plus? Means x is a little bit bigger than 2. If x is a little bit bigger than 2, means x squared a little bit bigger than 4. So that's why I wrote 4 plus here. So it means the reason I wrote 4 plus here is if x is bigger than 2, then x squared is bigger than 4. So that's why I wrote 4 plus. Now 4 plus means a number a little bit bigger than 4. For example, 4.1 or 4.01. So for example, 4 minus 4.1, how much is it? 4 minus 4.1 is minus 0.1. Right? 4 minus 4.1 is minus 0.1, or 4 minus 4.01 is minus 0.01. So 4 minus 4 plus is 0 minus. So this one I have to write it as maybe I can write here 11 over 0 minus. For example, I can write 4 minus 4.1 is minus 0.1, or 4 minus 4.01 is minus 0.01, and so on. So 11 over 0 minus, we saw that the answer is minus infinity. We already mentioned here that a fixed positive number over 0 minus is minus infinity. Okay, so the answer to this limit is minus infinity. Okay, so and still we can say, so the answer to the limit was minus infinity. Still we can say that of course x equals 2 is a vertical asymptote, because we saw that if the right limit or left limit, any of them, either infinity or minus infinity, we can still say that the limit, the number x equals a is a vertical asymptote. So we can also say Let x equals 2 is a vertical asymptote. Okay, let's look at another example. What about, let's say, if you have the same function, x squared plus 7 over 4 minus x squared, x approaches to minus 2 from right. What do you think about this one? X approaches to minus 2 from right. So again, if you replace, so it's minus 2 squared plus 7 divided by 4 minus 2 from right squared. So minus 2 from right means a little bit bigger than minus 2. For example, minus 1.9 or minus 1.99. So for example, if you have minus 1.9, you raise it to power 2. What do you get? Minus 1.9. So imagine minus 1.9, you raise it to power 2. So this one, you get a number a little bit less than 4, right? Because power 2 will kill the minus sign. And 1.9 to power 2 is a number a little bit less than 4. So this one will be 11 over 4 plus 7, 11. 4 minus here. Okay, so I can also mention here that if x is bigger than minus 2, then x squared will be less than 4. Let's say if x is bigger than minus 2, and of course less than 0, then x squared will be less than 4. X is a little bit bigger than minus 2 here. It's like minus 1.9 minus 1.99, so on, and x squared will be less than 4. Less x squared less than 4 means 4 minus. 4 minus means the number is a little bit less than 4. Now you have a number, you have 4 minus a number a little bit less than 4. Like 4 minus 3.9 or 4 minus 3.99. The answer will be 0 plus, right? For example, 4 minus 3.9 is 0.1, or 4 minus 3.99 is 0.01, and so on. And 11 over 0 plus will be plus infinity. So the limit when x approaches to minus 2 from right is plus infinity. Limit x approaches to 2 from right was minus infinity. So what I gave these examples to show you that this sign here, whether plus or minus, has nothing to do with this sign here, whether plus or minus. And they have even different meaning, because this one, when it's a minus infinity, means the number is a negative number, like minus 1,000, minus 10,000, and so on. But this one doesn't mean that the number is positive or negative. It means it's a notation that is used to imply that the number is a little bit bigger than 2. Or if you use minus, means the number is a little bit less than 2. It doesn't mean whether it's positive or negative. Of course, in this case, if x is bigger than 2, it will be positive. But for example, here, when we say x approaches to minus 2 from right, so from right, this plus means from right, means the number is a little bit bigger than minus 2, like minus 1.9 or minus 1.99, and so on. So the number still is negative, right? Like minus 1.9 is a negative number, or minus 1.99 is a negative number. So this plus here does not mean the number is positive. It means the number is a little bit bigger than minus 2, like minus 1.9, minus 1.99, and so on. And so what I'm saying is that this plus or minus sign here has nothing to do with this plus or minus here. So in this example, this was plus, this was also plus, By the previous example, this was plus and this was minus. Okay, so these are some examples for finding the limits or laws or rules to compute the limits.